Today I'm going to talk to you about how to measure the unloaded quality factor Q of a microwave resonator. Theoretically, it is the stored energy divided by the dissipated power, U being stored energy, omega is angular frequency, and because it's inversely proportional to the dissipated power, it makes sense then to say that it is a measure of the quality, small dissipated power, high value. A typical setup for Q measurement involves a sweep generator and an analyzer. They're usually integrated into a vector network analyzer. The sweep generator puts out a sinusoidal signal that has a time-varying frequency over a pre-programmed range. That signal is incident upon a resonator. The resonator has two ports, port 1 and port 2. Power goes through the resonator and passes on to the analyzer, which then detects the power and plots it against frequency on its screen. It's also necessary to know how much power is reflected off of each one of these coupler ports, and so if a directional coupler is placed between the sweep generator and the resonator, the reflected power can be redirected also toward the analyzer, resulting in a graph that is the opposite of the transmission. And so these S parameters need to be analyzed in order to come up with an expression for the Q factor. Beginning with the transmission, or the S21, which goes by several names. It can be called the insertion loss, in which case a symbol L sub I is sometimes used. So it's somewhat erroneously referred to as S21, which is actually a dimensionless number from the S parameter scattering matrix, but it can be calculated from the actual S21. And that is in decibels. The transmission is a Lorentzian bell-shaped curve, centered at the resonant frequency, which we'll call F sub R. It has a width, delta F, and that width is measured halfway down. So it is the full width at half maximum. And if you measure halfway down, you are going down 3 decibels. And so the full width at half maximum is also the 3 decibel bandwidth. So what you might normally think of as Q is the resonant frequency divided by that bandwidth. But that really is not the Q of the resonator. That's specifically the loaded Q. Loaded Q is the Q of the resonator with the couplers, and it will be smaller than the actual Q of the resonator if you made the coupling really weak, and that is called the unloaded Q. So this is the loaded Q. That's what a network analyzer measures directly. If you look at the reflection, so this is the power that comes back through the directional coupler, also called the return loss. Use the symbol L sub R perhaps, and it is again erroneously referred to as S11. No, S11 is a dimensionless fraction that's contained within the scattering matrix. It is 10 times the log base 10 of what really is S11. And it's in decibels as well. The reflection is a mirror image of the transmission, also centered at F sub R. Far away from the resonance, all of the power is reflected back, and so this is your 0 dB point. And this difference is the amount of reflection. I'll call it delta S sub 11 for now. It's measured in decibels, and we'll take it to be a negative number. It's convenient to convert this return loss back into a fraction. I'll just write the inversion of that expression. So what is displayed on your network analyzer and is referred to as S11 in units of decibels, decibels is not really a unit, is the return loss that I have in this expression. So I'll indicate that with S11 in decibels. So when I say S11 in decibels, I mean the return loss plotted on a network analyzer. It is again a negative number. People often refer to this expression as the magnitude of the return loss. Concerning this dip that happens at the resonator, then the deeper the dip, the stronger the coupling. And also the deeper the dip, the smaller the loaded Q will be. The unloaded Q is independent of the depth of this dip, but the loaded Q becomes lower as this gets deeper. That's a true statement if you're undercoupled. You can be undercoupled or overcoupled, and I'm only going to treat the case of being undercoupled, but I'll tell you a little bit about the difference here. Consider a resonant cavity. And in comes an antenna. This brings in the microwave signal through say a coaxial cable. And that coaxial cable just went through a directional coupler so that you can have your reflection. We will imagine an antenna at the end. The center conductor of the coaxial cable is extended into the cavity, a distance L. Now imagine you make that length L longer or shorter. You vary it, and you measure the depth of that dip as you vary it. I'm going to make a sketch of S11 as it appears on your network analyzer for 4 different cases. The first case is with L very short, and we'll make L a little bit longer, even longer, and then too long. So when L is short, the dip will be shallow. But if you make L longer, the dip will be deeper. You can make L just the right length so that the dip is so deep you could never see the bottom of it. It's roughly infinitely deep, maybe 100 decibels down. What happens if you make it even longer yet? I would call it too long, and your resonance gets very wide. These cases have names. If this is overcoupled, when the length is just right that you have an infinitely deep dip, that means that all of the power that comes down the cable goes into the cavity and none of it reflects back. That's critically coupled. In that case, the resonator is matched to that coaxial cable. These two are undercoupled. It's only when the dip has no depth that the loaded Q, which the network analyzer displays, equals the unloaded Q on both of the couplers if there are 2 couplers. Of course, the problem with that is then you can't make a measurement because no power is going in. So you'll always have some power going in. In the measurements I'm talking about today, there are 2 couplers. One is an input, one is an output. I'm going to call them coupler 1 and coupler 2. Port 1 and port 2. One of them is S11, but the other one we'll call S22. And an unloaded Q measurement involves measuring the loaded Q and measuring these dips for each coupler port. Those are the measurements that need to happen. And each port has a different amount of coupling, and it can be characterized with the coupling coefficient. I'll use the letter beta to indicate it, and so there's beta 1 for port 1, and there's beta 2 for port 2. And they're calculated from the magnitudes of S11 for each dip. And the total coupling coefficient is just the sum of the 2. Physically, the sum of those 2 is the ratio of power dissipated externally to power dissipated internally. Combining all of this together to give you unloaded Q equals the loaded Q, where the loaded Q is measured by the network analyzer. It's the resonant frequency divided by the 3 dB width. It's the full 2-port method. There's a second method that involves transmission, which can give you the unloaded Q of a resonator. Besides the full 2-port method, there's the insertion loss method. The insertion loss measured on the network analyzer for a resonator is this Lorentzian-shaped bell curve, and the expression for Lorentzian in decibels, the insertion loss, is where F is the frequency and F sub r is the resonant frequency. I quickly comment that loaded Q is always smaller than unloaded Q. So the contents of this logarithm is always a positive number, but it's also always the logarithm of a number greater than 1. L sub I is a positive number. We have to keep this in mind, that when we talk about L sub I, we're talking about a positive number in decibels. When f, the frequency, equals the resonant frequency, when we are right here, this second term is 0, because it's 1 plus 0, right? When f equals f sub r, this parenthesis comes out to 0, and you're just taking log base 10 of 1. So this term is 0 when you're at resonance. Well, good. Then what you do is you measure the insertion loss at resonance and immediately calculate the ratio of loaded to unloaded Q. The insertion loss at resonant frequency, 20 log base 10. To make things less tedious, I'm going to invert the argument inside the logarithm. That's okay to do if at the same time I put a minus sign outside. And then invert this expression for unloaded Q equals, so raise the number 10 to both sides of this equation. So if L sub I equals that, then 10 to the L sub I equals 10 to that. And we have this working equation. I'll illustrate how you measure that with a little picture. Your network analyzer screen will have the bell curve, the S21, centered at f sub r. And in order to know what L sub I is at f sub r, you have to know where the 0 is. So that's 0 decibels of insertion loss, and this amount is the insertion loss at the resonant frequency, which we use in this equation as a positive number in decibels. So it should be clear that the insertion loss method requires that everything outside of the resonator itself has to be zeroed out, so that when you measure the insertion loss, you're measuring the insertion loss of the resonator. So let's go into the laboratory now and actually use both of these methods, the full two-part method and the insertion loss method, to determine the Q of a resonator.